In this video, we're going to prove 5 facts about the trace of a matrix. Just to review, to talk about a trace of a matrix, the matrix must be square. And the trace is very simple to compute. You just add up the numbers on the diagonal. So if this was matrix A, then the trace of matrix A would be 3 plus 2 plus negative 2, which is the number 3. It has to be a square matrix. Okay, so let us do the proof of A. Proof of A. Okay, so the trace of this matrix is the summation of the entries on the diagonal, which is C times, no, I'd rather prove it the other way. I'm gonna start with C times the trace of A. So this is C times the summation of AII as I goes from 1 to N, an N by N matrix. But this here is the same as the summation as I goes from 1 to N of C times AII. But that's just the trace of CA. Because this is the elements on the diagonal of C times A. That completes the first proof. Now we want to prove this. Proof of B. The trace of A plus the trace of B. Well, the trace of A is the summation as I goes from 1 to N of AII. The entries on the diagonal. Add them up. Plus the trace of B. Everything is an N by N matrix. So it'll be the summation of BII as I goes from 1 to N. But this is the summation as I goes from 1 to N of AII plus BII. But this is the summation of A plus B, the II entry, as I goes from 1 to N. And this is equal to the trace of A plus B. Maybe in the last proof I can insert one more line. CAA is the same as the II entry of CA. And that is the trace of CA. Okay, that's letter B. Letter C, we want to show that the trace of our product commutes. proof of part C. The trace of AB is the summation of AIK, BKI, because I and J are the same. AIK, BKI. As I goes from 1 to N. Okay. I meant to say K goes from 1 to N. Apologize. Now, that's a bit interesting. Okay, so we need to say a little bit more here. K goes from 1 to N. This here is the II entry of AB. That is the II entry of AB. Now we need to sum them all up. And this is as I goes from 1 to N. K goes from 1 to N. Okay. Now we have the summation as I goes from 1 to N of the summation as K goes from 1 to N of this. But those are real numbers. This is the same as B, so the real numbers commute. I can switch to A and to B. This is the same as BKI times AIK. Now, K goes from 1 to N, I goes from 1 to N. If I call those K and I call those I's, it wouldn't matter, because K and I are both going from 1 to N. So this is the summation of double summation of BIK times AKI. Where maybe now we'll switch the I and the K here. Summation as I goes from 1 to N, summation as K goes from 1 to N. But this is the trace of B times A. That is the proof of letter C. Letter D wants us to show that the trace of A transpose is the same as the trace of A. So, proof of D. The trace of A transpose, well, this is just the summation as I goes from 1 to N of A transpose II. I goes from 1 to N. Now, if I switch the row and the columns, I get A, and I also get II. Switch I and I, you still get I and I. So this here is the summation of, excuse me, that is the trace of A. Just add up, those are elements in A, and just add up, those are the diagonal entries of A, and just add them all up. A11 plus A22 plus A33, you get the trace of A. The last proof is to show that the trace of A transpose times A is at least 0. Now, okay. Proof of E. The trace of A transpose times A. Okay. So, this is the sum of the diagonal entries. K goes from 1 to N. We have A, I, K. Well, this is just going to be the AII. The II entry. It's going to be the II entry of this. Okay? Transpose times AKI. Now, if you sum up over K, you just get the A transpose, you get the diagonal entry of the II position for A transpose A. But we want all of them, not just I. So we'll let I go from 1 to N. Okay. Now, this here is equal to the summation as I goes from 1 to N of the summation as K goes from 1 to N of. Now, that is the same as AKI. I switched the I into K, so I dropped the transpose. Times itself. Times itself. So this is the summation as I goes from 1 to N. The summation as K goes from 1 to N of AKI squared. But this is computing this first. This is the summation as I goes from 1 to N of A1I plus A2I all the way up to A sub Ni. And of course I have one thing very wrong. These are all squared. So all I did was let K be 1, then I let K be 2, and 3, and 4, all the way up to N. Now, when I sum over the i's, so now the i's change. First I is 1. I get A11 squared plus A21 squared all the way up to A sub N1 squared. Now I is 2. So I get A12 squared, A22 squared, all the way up to a N2 squared, and so on, all the way until I is N. So I get a 1N squared plus a 2N squared, all the way up to a and N squared. Okay. Now, since each of these entries are real numbers and you square them, the least you can get is 0. This term greater than or equal to 0. That term greater than or equal to 0. All of the terms, greater than or equal to 0. Greater than or equal to 0. All the way down to the last one, greater than or equal to 0. You add them all up, you're going to get at least 0. How do you get 0? If they're all zeros. That completes this proof. If you like videos like this, subscribe to my channel, leave a comment saying how much you hate my videos or how much you love my videos. If you like to see a theorem proved, please leave that in the comment section. And as always, most of all, watch and learn. See you in the next video.